Hello and welcome to our video teaching lesson for Math 171, actually on two sections this time, section 3.2 and section 3.3, with 3.3 having a good deal more content, so more of our time will be spent on 3.3, but we're going to start off with 3.2. So again, unfortunately, technical issues with the iPad interface, so I'm again restricted to using what's available on screen with the textbook and such as that. So I cannot actually work out problems in front of you, but I can talk about things, so hopefully this will be helpful. I'm confident it will be. So section 3.2 is about polynomial functions of higher degree. We had our last online lesson on section 3.1, which was quadratic functions exclusively, and now we're moving past functions of the second degree, where the highest exponent is only a 2, with only having x being squared. We're now moving on to x to the third, x to the fourth, x to the fifth, etc. And honestly, primarily we will remain not going higher than x to the fifth if I remember the problems we have coming up here. So going on past x squared, there are some common characteristics of the graphs of polynomial functions of various different degrees, regardless of how high or how low they are. For instance, if the degree is an even number, like it has x squared, x to the fourth, x to the sixth, or if the degree is an odd number, like x to the first, x to the third, x to the fifth, x to the seventh, there are significant characteristics of those two groups of functions. We're going to talk about that. But first, let's get into some basic characteristics of polynomial functions at all. The simplest polynomial functions we've discussed already, where it was just x to the first and then x to the second, and you can even have just x to the 0, which is where the f of x is simply equal to a constant. And that constant, as you see here, like f of x equals a, that's actually a times x to the 0 power. And of course, we will recall that anything to the 0 power is 1. Even x, an unknown to the 0 power, is 1. So it's actually a times x to the 0 if you like to think of it that way for consistency. But it's just f of x or y is equal to a constant. And as we all know, that's just a horizontal line. Its graph is. Then if you have x to the first in the form of f of x equals ax plus b, or as we're more used to denoting it, mx plus b, where the slope of the line is the coefficient of x and b, the constant, is the y-intercept. That is a first degree polynomial function. Second degree is f of x equals, in classic general form, ax squared plus bx plus c. And interestingly, that constant c, once again, is the y-intercept, because when x is equal to 0, all the x terms, whether they're squared or whatever power it is, all go to 0, and the only thing you have left is c. So that constant at the end for all of our polynomial functions in this chapter, that constant at the end is going to be the y-intercept. Now, one characteristic that all polynomial functions have is that they are what we call continuous. That's actually a technical term in math. Continuous means, so to speak, that if you were to draw the graph on paper using a pencil, that you never pick up the pencil, move somewhere else, and then start writing again. There's no skips or jumps or holes or anything like that, no breaks in the graph. So this one on the left is showing a portion of a graph which is continuous, and the one on the right is showing a graph that is discontinuous. It is not continuous because of this skip right here, this break between these, the black filled in circle and the white filled in circle. There's a gap in the graph there, so that function is very simply not continuous. It's graph. Now here's the good news. if we are dealing truly with a genuine polynomial function, no matter what its degree, it is continuous. There are no such things as vertical asymptotes. There are no holes, no skips, no gaps, no breaks, no jumps with any polynomial function of any degree. Now you say, well, what about vertical asymptotes? Well, that comes in the last two sections of this chapter, 3.5 and 6, talking about rational functions, where we have actually one polynomial divided by another one. And yes, then you have times where the denominator is 0 and you can have either vertical asymptotes or holes. And we will get to that here before too long, actually, in the near future. So what do we have right now? We're talking about graphs being continuous. Another interesting thing about polynomial graphs is not only are they continuous, but they never have a sharp corner in their graph. Their changes are always smooth as you draw the curve. For instance, like this one on the left here, you draw that curve and it's not only continuous, but it's smooth. It's never a sharp corner as this one on the right is, where it's virtually looks like a right angle there. Well, regardless what angle it might be, there is no such thing as a sharp turn, sharp corner like that for any polynomial function of any degree. It just doesn't happen. This right here, for instance, could be the graph of some type of absolute value function, classic V shape like that, but it cannot be a polynomial function with a sharp corner like that. Now, we're going to start off with what we call simply power functions. And these are where f of x is simply x to some power of any positive number. Say x to the first, second, third, fourth, fifth, sixth, seventh, whatever, but that's it. There's no coefficient in front of the x to the power other than 1, the invisible 1 coefficient. And there are no other terms following x to that power. The entire function is just x to that power, like y equals x cubed, y equals x to the third, y equals x to the sixth. Those are called power functions. And the first one of these we get to as we leave quadratics behind, so to speak, is x to the third, which does have a name, the cubic function. And a few characteristics of this function itself is being a function, of course, it has a domain and a range. And with x to the third, the graph passes through the origin and it goes down to the left forever and up to the right forever. It actually only exists in the first and third quadrants. It has not a single point in quadrant 2 or quadrant 4. It's entirely in quadrants 1 and 3, except for the single point, the origin, which is where the axes meet. And the axes, of course, are not in any of the quadrants. They delineate the quadrants. So it's all in quadrant 1 and 3 in the origin. It is an odd function. If we were to fold either of these portions of the graph across the x-axis and then across the y-axis, they would be right on top of each other. They're exactly opposite. Every single point in the quadrant 1 portion, for instance, is exactly opposite from another point in the quadrant 3 portion of the graph, same distance away and on the same line passing through the origin even. It's kind of interesting. That's an odd function. But its domain and range are both absolutely infinite and unlimited. So the x values that work with y equals x to the third, f of x equals x to the third, whichever way you say it, are from negative infinity to positive infinity. And the y values are also from negative infinity to positive infinity. No restrictions, no limitations, no exclusions. Absolutely unlimited infinite domain and unlimited infinite range. And it only has one intercept. The x-intercept is the y-intercept. It's the 1-intercept 0, 0, the origin. Interestingly, it's increasing on every single interval upon which it exists. So it's increasing everywhere, we say. This function never goes down to the right. It doesn't even stay constant to the right. It's always increasing as x increases, y is always increasing as x is increasing. So the entire function is increasing everywhere. That's y equals x to the third. Now, another point here, if we insert a minus sign in front of x to the third, what's going to happen? If we try to graph y equals negative x to the third, what that does is reflect the whole graph. That does cause a reflection. I can do this. We can bring up Desmos here. And I can graph, for instance, y equals x to the third. And then also graph y equals negative x to the third. We got to do some things to our scale here from what I've been doing with this just a while ago. Okay, let's get this back here now. All right, now zoom back out again. There we go. Okay, so the one that's sort of purplish color coming up from the lower left here as I'm tracing now and going through the origin, and sort of actually does kind of level off there just for an instant, and then goes back up steeper and steeper forever and ever up to the right. That's y equals x to the third. The one that is a vertical mirror image of this reflected across the x-axis is y equals negative x to the third. It's coming down from the left and going through the origin and then going down to the right forever in quadrant 4. So y equals negative x to the third exists exclusively in quadrants 2 and 4 and the origin point. And it's interesting, graphing both of them together here, it almost looks like one parabola on top of another with their respective halves, horizontally speaking, paired up. But they're not parabolas because that would have to be an x squared situation. These are x to the third situations. So, but that's what happens. The negative sign inserted in front of the term of the highest degree, in this case, of course, the only degree, the third degree, reflects the entire graph across the x-axis. And also what that does, let's talk about this. What that also does is it causes it, instead of coming up from the lower left and going up to the upper right, it's coming down from the upper left and going down to the lower right. And so it's decreasing everywhere. As y equals x to the third is increasing on every single interval, y equals negative x to the third is decreasing on every single interval. And here's the classic pattern class. For anything with an odd number exponent. Let's go back and even do just y equals x to the first. I'll write it as x to the first, but we all know it's redundant. All you have to do is say y equals x. That's the same thing. And notice we know that line, of course, the identity function going through the origin, y equals x from the lower left to the upper right. That's my point with this, because it actually is an odd numbered exponent on this first of the power functions with a positive exponent on x. It is, just like x to the third, coming up from the lower left and going off to the upper right. In that sense, its behavior is like x to the third. Of course, it's a straight line as opposed to a curved line, but it is coming up from the lower left and going up to the upper right, and it only exists in quadrants 1 and 3, just like x to the third. But what if we go up to x to the fifth? In fact, I'm going to delete this x to the negative x to the third now. Let's go y equals x to the fifth one more time with an odd exponent for a power function. And now this is sort of in a pinkish red color. you'll notice it's similar to y equals x to the third, but it comes up more steeply from the lower left and goes up more steeply to the upper right. Still going through the origin, of course, still only in quadrants 1 and 3. But it's, again, coming up from the lower left and going up to the upper right. Or as you might say, if you make your perspective point be the origin, you can say it goes down to the left, going to the left, of course, and going up to the right. And this is the ultimate end behavior of every polynomial function of odd degree that has a positive coefficient on the leading term, the term with the highest degree. Okay, making a statement here. This is the behavior of every polynomial function of odd degree, that its highest term, the exponent on x, is an odd whole number like 1, 3, 5, 7, 9, 11, etc. And the coefficient of x doesn't have to be just 1, but it does have to be positive. It could be 3x to the fifth, 17x to the third, whatever. It's still going to come, the graph is going to go down to the left and up to the right. And that exactly becomes opposite if you put a minus sign in front of the term of highest degree. So if we made it negative x to the fifth, for instance, if we did that, then if I put a minus sign in there, it flips it just like that. And if I delete it again, you can watch it going away and coming back. And there's with no minus sign, there's a minus sign, and etc. So it literally just causes it to reverse which direction it goes, off to the left and off to the right forever. And by the way, this ultimate direction which it goes is true regardless of how many other terms we have in here. So for instance, if we had y equals 4x to the fifth minus 3x to the fourth plus 2x to the third minus 6x squared plus 2x minus 1, say. Okay. Well, there's the graph of that thing. And what you can see is, even though it's got a little blip right in here, still it goes down to the left forever and up to the right forever. And you can see that even more so if I bring out the scale here. So it's obeying the rules that we are presently discussing. And if all I do is put a minus sign in front of the leading coefficient of 4, keep everything else the same, watch what happens to this one here. And then it goes the other way. It goes up to the left forever and down to the right forever after it has this little blip in between here. Okay. All right, so what about even degree functions? Well, let's eliminate some of these here. And if we have like y equals x squared, well, interesting difference here. It no longer goes infinitely down or infinitely up. It only goes infinitely up, and that's it. So it goes up to the left and up to the right. It does not go down at all. It has, in fact, a minimum point right at the origin of 0, 0. That is its minimum point. We also call that the vertex, of course, for a parabola. And this is going to be a consistent property of all polynomial function graphs if the leading coefficient is positive, the coefficient on the term of highest degree, and if the exponent on the term of highest degree is even. So let's go up to y equals x to the fourth. Okay, this is a sort of a modified parabola. It looks more level here. It's not actually level, but it's leveler than the y equals x squared. And that's actually, once it gets past 1 and -1 to the right and to the left respectively, it goes up faster. It goes up faster than x squared does. But notice it goes up to the left and up to the right. That's the point. And if you had y equals x to the sixth, it's still going to do that. So it goes up even more steeply to the left and more steeply to the right than x to the fourth or x squared. And once again, it has a minimum point. And we all know what happens if we change the sign here. If we make it y equals negative x squared, then instead of opening upwards, the parabola opens downwards, and that's going to be true with all these. Whether it's x to the second, x to the fourth, x to the sixth. If we put the minus sign in front of it, there's negative x to the fourth. It has a maximum point now, and it goes down to the left and down to the right. So here's the point. If you have a polynomial function of even degree, then ultimately it might have a few blips in the middle, but ultimately it's going to go the same direction to the left and to the right, either both up or both down. Either both up to positive infinity or both down to negative infinity eventually. That's if it's positive degree. It's going to go the same way, same direction, either both up to the left and the right or both down to the left and to the right for a polynomial function of even degree. And they will both go up if the leading coefficient is positive. They will both go down if the leading coefficient is negative. Now, as we saw just a few minutes ago, if the term of highest degree is an odd number, like x to the first, x to the third, x to the fifth, then going off to the left ultimately and off to the right ultimately, it's going to go different directions. It's going to go down one way and up the other way. In fact, that's an absolute clue that its exponent on the term of highest degree is an odd number. And once again, if the leading coefficient on the term of highest degree, and you write all the terms in descending order, the highest exponent first and all the way down to the constant, what we call the leading coefficient, the coefficient of the term of highest degree, if it's positive on an odd degree polynomial function, then the function will ultimately go down to the left and up to the right. But if the leading coefficient on the term of highest degree is negative, it will go up to the left and down to the right. With the key point that if it's an odd degree polynomial function, ultimately off to the left and off to the right, it goes opposite directions. It goes two different ways. One goes up and one goes down, whichever one it is. And again, with even exponent polynomial functions, they either both go up or both go down, ultimately to the left and the right. So, some basics of understanding the graphs of polynomial functions of higher degree. And what we're saying about these things, class, interestingly, is unchanged if we add additional terms after the term of highest degree, as long as they're lower degree terms. To the x to the fourth function, we could add x to the third and x squared and all that, and still ultimately, if we keep the exponent on x to the fourth positive, say make it 3, then no matter what we put after this, it is still going to be, let's see if I make that a bigger number if it makes a difference. And then, yeah, there we go. Now we've got a couple of blips in here, so to speak. It comes down from the left, hits a minimum point. In fact, it looks like right on the x-axis there. And it goes back up again a little bit, and then down again, and then it only goes down so far, and then comes back up again. And my point is, as I'm saying, this is an x to the fourth function with a positive leading coefficient being 3. And so that means, without even looking at the graph, even with all these other terms after it, it's not going to make any difference. It's still ultimately going to behave basically the same way. Oh, okay, there we go. That actually made it less interesting, so let's delete that part. Yeah, so now we got that little blip in there, as you can see. And ultimately it goes up to the left and up to the right, as it must, being a polynomial function of even degree, in this case 4, and the leading coefficient is positive. So that means it has to go up to the left, it has to go up to the right eventually, even though it has a few blips in here in the middle. By the way, the number of times the graph can change direction from increasing to decreasing or decreasing to increasing is always the maximum number of times it can change. Maximum is always 1 less than its degree. So this one with an x to the fourth can only change direction 3 times, and we see that. Coming down from the left, it's coming down, it's decreasing, then it briefly increases, then decreases, and then increases again. So it goes from decreasing to 1 change increasing, second change decreasing, third change increasing. The number of changes in decreasing versus increasing, whether it's the graph's going up or down, is always 1 less than its degree, or some multiple of 2 less than that. So we could either have these 3 changes of direction, or we could just have 1 change of direction, as we have if we eliminate all those terms and just have that. Y equals 3x to the fourth. Now there's only 1 change of direction. It was decreasing, and now it's increasing. So some basic interesting stuff about polynomial function graphs. And let me get back to the other now. Okay, here we are. Okay. There's a good chart which briefly summarizes what we've been talking about now here for a few minutes. Briefly summarizes it here. On page 256 of your text, the leading coefficient test chart here, and it's telling you just what we've been talking about here. That if the leading term's exponent n is odd, then when the leading coefficient is positive, it behaves like this. And if the leading coefficient is negative, it behaves ultimately up to the left and down to the right, like that one. And if it's even, if you have an even exponent, then ultimately it goes up to the left and up to the right if the leading coefficient is positive, and it ultimately goes down to the left and down to the right if the leading coefficient is negative, just like we've been talking about. Now, I also want to show you this. This is a term we haven't used a lot yet, but we're going to start using it some more. Zeros of polynomial functions. So zeros of polynomial functions is going to turn out to be basically like when we were trying to find solutions to equations earlier in the course. It also coincides with the x-intercept values, the x numbers that are the x-coordinates of the x-intercepts. Those same numbers, which are also solutions of equations, we're now going to call them zeros of the functions. Which means that if you have any function f of x, and if you set it equal to 0, specifically equal to 0, and then solve for x, the different values of x that will make that whole polynomial equal 0, we previously called those solutions of the equation. Well, now we're going to call them a new term, zeros of the function, because these are exactly where, when we graph the function either touches or crosses the x-axis. They're the points at which the graph of the function has a y-coordinate of 0. It's right on the x-axis. And so these x numbers are the x-intercepts. They're the zeros of the function. They're solutions of the polynomial equation when we set f of x equal to 0. And one more thing, like this little chart says, if you take whatever that x value is, that is the solution or the 0 or the x-intercept number, they're all the same. Here they call it a. If we take those numbers, then that number a, and subtract it from x, that expression itself, x minus a, typically in parentheses, is what we call a factor of the polynomial f of x, meaning that it will divide evenly into the polynomial. So if we take the entire polynomial, no matter what its degree, and divide it by x minus that solution 0 x-intercept number a, x minus that number a, it will come out evenly in the division without any remainder. Interesting fact that whenever a certain number is a 0 of a function, then x minus that number is 100% of the time a factor of the polynomial. It works both ways. And if x minus a is a factor, then a is a 0. And that's what this little chart is telling us, class. Mathematically, when we say a statement is equivalent to another, and we're making the claim in this little box, which is a true claim, that all four of these statements are equivalent, that simply means mathematically, to say they're equivalent, it means that they give us the same mathematical information. To say that x equals a is a 0 of the function f tells us the same information as saying that x equals a is a solution of the equation, or x minus a is a factor, or a comma 0 is an x-intercept of the graph of f. All of those tell the reader the same, exactly the same mathematical information. It's just stating it in different terms. We're going to speak much now for the rest of this chapter about both zeros of functions and factors. These parentheses, x minus the number factor of polynomials. So you're going to have quite a few homework problems where you're going to be finding zeros of polynomial functions. And oftentimes you want to factor these things if you can. If you can reduce them down to something, for instance, times a quadratic, then once you can get it down to just a quadratic, you can solve a quadratic, if nothing else, by the quadratic formula. And so, for instance, this one right here, example 4, f of x equals x to the third minus x squared minus 2x, has the common factor of x in all three terms, so that x gets factored out to the front as the GCF, the greatest common factor, leaving parentheses x squared minus x minus 2 as a quadratic factor, as we call it. And then that nicely can be factored itself into x minus 2 and x plus 1. So now that the polynomial has been factored, that tells us the three zeros. Just the term x by itself always tells us that the number 0 is a 0 of the function. In other words, x equals 0 is a 0 when x itself is a factor, because when you think about it, just the x by itself really means x minus 0. We could rewrite this x right here as x minus 0 in parentheses times x minus 2 times x plus 1, and it's always the number being subtracted from x, which is the 0. So 0 being subtracted from x, 0 is a 0. 2 subtracted from x, so 2 is a 0. And x plus 1 actually indicates that negative 1 is being subtracted from x and written as x plus 1. So the three zeros then are 0, 2, and negative 1. This next one right here is a little bit interesting. Example 5, f of x equals negative 2x to the fourth plus 2x squared. This one's, I say, interesting because it has a common factor in both the terms of not even just x, but x squared. And we can even pull out negative 2 also. But the x squared is what's kind of significant, because that x being squared, class, you must remember that's actually meaning x times x. So it's actually x minus 0 parentheses times x minus 0 parentheses, and then times factoring out the x squared minus 1 into x minus 1 x plus 1. We actually have 4 factors: x times x minus 1 times x plus 1, which gives us 4 zeros. Now only 3 are distinct numbers. The only 3 numbers that we have that are zeros of the function are 0, negative 1, and 1. However, the point is, the number 0 is what we call a repeated 0 of multiplicity 2. Multiplicity is the term that simply tells us, it's a mouthful of a word, but it simply tells us how many times that particular number is a 0 of the function. So in this case, 0 is a 0 of our given fourth degree function 2 times. Now, what does that mean when we look at the graph? How is this going to reflect on a graph of a function if a certain number is a 0 more than once? And that is very interesting how this works out. We can see the graph of this particular function right here, just to the right of the problem. It's a fourth degree with the leading coefficient being negative, which tells us, even before we graph it, it's going to go down to the left forever and down to the right forever, but it's got this little blip right here in the middle where it comes up from the left and then down and up and then back down again. And this little portion right in here that's different, right in the middle there of the function, so to speak, that portion right in there does something interesting in that it reaches this relative minimum point right in here, which is dead on the x-axis. It's right at 0, 0. Now, what does that mean? The point I'm making is that the graph of this function does not, it comes up and it crosses the x-axis at x equals negative 1. It goes up to this maximum point, this relative maximum point right here, then back down to precisely just touching the x-axis at the origin. It does not cross the x-axis. That's the point. It just touches it and goes back up again to another relative maximum point, and then down, crosses the x-axis, and then goes down forever to the right. Now, what's different in the 3 places that it makes contact with the x-axis? At x equals negative 1 and x equals positive 1, the graph of the function actually crosses the x-axis. Either comes from below it to ending up above it, or it comes from above it to ending up below it. But that's not what happens at the middle x-intercept, at x equals 0. It simply comes down from above, just glances on the x-axis here, just barely touches it, and goes back up again without crossing it. And here's the point of that, class. If you see a graph like this where a certain function either comes down from above and just touches the x-axis, and then moving to the right, it goes back up again. Or if it comes from the left and from below, it comes from down below up to the x-axis and just touches it and goes back down again without crossing it. In those cases, you know that whatever the x-intercept value is there, that x number is going to be a zero of the function an even number of times, not an odd number of times. In fact, it cannot be a zero of the function just one time. It has to be either 2 times or 4 times or 6 times and something like that, an even number of times. And similarly, class, if the graph of the function crosses the x-axis at a certain point, then either going up or coming down, it goes all the way across it, then that tells you that the x-intercept indicated there and the zero that's indicated at that x value is of multiplicity of an odd number. Either that zero is a zero 1 time or 3 times or 5 times or 7 times. And I will tell you this, generally speaking, most of the problems we're going to deal with in this chapter, if it's an odd number, it's usually 1. If it's an even number, it's usually 2. Most all the time for the problems that we're going to do. But that's very interesting how that works out. It works both ways. If the graph is like this, then that tells you about the multiplicity of the zeros. And if you know the multiplicity of the zeros, then you know what the graph's going to look like. If the multiplicity of a 0 is 2, then you know that the graph is only going to touch the x-axis at that x value and not cross it. Okay. So let's move on now to section 3.3. And when we start speaking of something being a factor of a polynomial, then we're really talking about multiplication or its converse operation, the opposite operation of division. And if some number evenly divides into something else, then we say it's a factor of that other quantity. For instance, 3 times 4 is 12. So 3 is a factor of 12 and 4 is a factor of 12. And you can do it backwards. A factor means that it multiplies to make it, but it also works just the opposite. Since 3 and 4 are factors of 12, then 12 divided by 3 is going to give you an answer with no remainder, and surely it does. 12 divided by 3 is 4, no remainder. And since 4 is a factor of 12, 12 divided by 4 also gives you no remainder. It's just 3, remainder 0. So that's what we mean by factors, actually. And this is really interesting stuff, but polynomial functions, polynomials themselves behave very much like the integers do, the numbers that we're used to working with. They behave very much like integers in that they have factors. And you can, just like integers, if you add one polynomial to another polynomial, you get a polynomial. Just like if you take an integer and add it to an integer, you get an integer. If you subtract one from one, you get another polynomial. If you multiply a polynomial times a polynomial, you get a polynomial. Multiply an integer by an integer, you get an integer. However, it breaks down for both of them with division. If you take a polynomial and divide it by another polynomial, you may or may not get a polynomial. You may get some kind of rational function. It may not be a polynomial at all. Just like an integer divided by an integer is not necessarily an integer. If you take 3 divided by 5, that's 3/5. It's not an integer. So it's interesting how they're similar. So just as we can do what we learned years ago when we were all very young, we learned about short division and long division using integers, actually using the positive integers, the counting numbers. we're now going to talk about doing long division with polynomials. And I'm confident some of you have seen this before, but perhaps some have not. There's a couple of good examples here in the book about this. We actually follow a technique so very, very similar to long division of integers. And so, for instance, if we wanted to do like example 1, divide 6x to the third minus 19x squared plus 16x minus 4, divide that cubic polynomial by x minus 2. Here's what happens. We write the, just like we did years ago with long division, if you had a number with 4 digits, you would work with each digit separately, and this is a polynomial with 4 terms, sort of comparable to 4 digits, and we work with each of those terms separately. And we divide this polynomial with 4 terms by one only having 2 terms. And it's kind of like dividing a 4-digit number by a 2-digit number back when we were in elementary or middle school. And here's how you do it. You take it one term at a time. So starting to divide the x minus 2 into the big cubic polynomial, we ask ourselves, first step, how many times will just the x, not the x minus 2, but just the x of the x minus 2, how many times will that x divide into 6x to the third? And of course, 6x to the third divided by x, just subtract the exponents, 3 minus the 1, you get 2, and it goes 6x squared times. So 6x to the third divided by x is 6x squared. And you write that up on the top. These are what we call our partial quotients, each of these terms up here. And now we come back and multiply the 6x squared times the x and times the minus 2, just like we would have done if these were digits in long division. So 6x squared times x is 6x to the third. We write it right under the x to the third term. 6x squared times negative 2 is negative 12x squared, and we write that right under the x squared term. Now we do just like we did previously with 2-digit numbers. We subtract. So we subtract the 6x to the third from 6x to the third, and it's gone. It's 0. Don't even write the 0 down. And now here's where you have to watch your signs carefully. Now we're going to subtract negative 12x squared from minus 19x squared. So subtracting negative 12x squared is really like adding 12x squared to negative 19x squared. So negative 19 plus 12 remains a negative 7x squared. That's the result of the subtraction. So we write down the negative 7x squared here, and then just like long division years ago, we go up and bring down the next term. In this case, plus 16x. All right, now we repeat the process. Start all over again. Ask ourselves, how many times does x go into negative 7x squared? And it goes negative 7x times. We write that up as a second partial quotient up here now. And then we multiply negative 7x times x and times the minus 2. One piece at a time. Negative 7x times x is negative 7x squared. Negative 7x times negative 2 is positive 14x. And once again, we subtract both of these terms from their respective like terms right above them. The negative 7x squareds cancel out. And 16x minus a positive 14x is just 16 minus 14, 2x. And yes, once again, bring down the next term, minus 4. Start the process all over again. So x goes into 2x 2 times. And we put it up here, plus 2. That's the final piece in our partial quotient list. And now we multiply 2 times the x and 2 times the minus 2. So 2 times the x is 2x, 2 times the minus 2 is minus 4. And yes, we subtract 2x minus 4 from 2x minus 4. Well, anything minus itself is 0, so the 0 gets posted here as the remainder. The remainder technically is 0, or as we often would say it, there is no remainder, but the remainder is 0. And so that means that dividing 6x to the third minus 19x squared plus 16x minus 4 by x minus 2, the answer is this quadratic polynomial. That's the quotient. That's the answer to the division problem. It's exactly 6x squared minus 7x plus 2. Following the same process we used to do with multi-digit numbers, now this is multi-term polynomials, following precisely the same processes of divide, multiply, subtract, and bring down the next quantity and all. Same procedure. And of course, it doesn't always come out to zero remainder. It could come out to something. It could come out, if this had been up here at the original third degree cubic polynomial instead of minus 4 here, if that had only been, for instance, if that had been minus 5, then we would have had minus 5 minus a negative 4, and it would have ended up being minus 1 as a remainder. If it had been minus 3, you'd have minus 3 minus a negative 4, it ended up being positive 1 as a remainder. So you can have remainders. And typically what we do, and WebAssign will expect you to do this when you submit your answers for homework problems in WebAssign, it's going to expect you to enter any remainders, just like we had to do starting, what, around 4th grade or so. We couldn't just put R period the number. You had to make the remainder into a fraction, if you recall. And so if there was a remainder, you would put the remainder, whatever number it was, over the divisor as a fraction. In this case, it would be the remainder over x minus 2. So like I said a minute ago, if this was 6x to the third minus 19x squared plus 16x minus 3 instead of minus 4, then we'd have a remainder of 1, and the answer in that case would be, the answer would be 6x squared minus 7x plus 2 plus 1 over x minus 2. That would be the answer that you would put into WebAssign for the answer. Okay. Now, having shown you all that, I want to make one more point about polynomial long division and then show you a much simpler way to do this that in many cases will work and make it simpler. But let's look at one more problem here just briefly. If we were asked to divide, as in example 2, 8x to the third minus 1 by 2x minus 1, well, you notice 8x to the third minus 1 has several exponents missing. There's no x squared term and there is no x term. And so what we're obligated to do, what we must do to correctly follow the process of long division is the same thing we used to have to do with numbers. If you divided 1001 by 12, you don't just write the 1001 as 11. You have to hold those spaces in between with the zeros. The 0 in the hundreds place and the 0 in the tens place for 1001. So you would divide 1001 by 12. And that's what we have to do here. The 8x to the third minus 1, we have to make it 8x to the third plus 0x squared plus 0x minus 1. This is not an optional step. We have to do this or we won't get the right answer. And so when you do all that, then you just follow through the steps as we just did on the previous problem. It just comes down just fine. Once again, this one comes down to a remainder of 0, telling us that 2x minus 1 actually evenly divides into 8x to the third minus 1, and it does. It goes 4x squared plus 2x plus 1 times. Now, let's look at a shortcut for this procedure. Some of you have seen this before, but I'm guessing many perhaps have not. It is a process known as synthetic division, which somebody very cleverly came up with. Probably somebody who for some reason had to do a lot of polynomial long division, and they started noticing some patterns in the process. and applied some very clever thought to it and came up with a much simplified system of accomplishing polynomial long division, in which we do not have to write the x's, we don't have to write the exponents, we only use the coefficients of the terms. And interestingly, even more so, as we all know, addition and subtraction are opposite operations, and multiplication and division are opposite operations, but intrinsically, inherently, adding is easier than subtracting, and multiplying is easier than dividing by their very natures. So whoever came up with this process said, let's just change this all around, and instead of having to subtract, let's make it where we add. Instead of dividing, let's make it where we multiply. It's an amazingly simple system. So here's what you do. If you want to divide, for instance, like this explanation box shows us, and then we'll go through a real one. If you want to divide ax to the third plus bx squared plus cx plus d by x minus k, so you got a cubic polynomial divided by a first degree polynomial, just x to the first minus k, then what you do is, starting with the ax to the third polynomial, which has 4 terms, we strip off the x's and the exponents. Now you must have them all written in the correct order, from the highest exponent coming down one exponent at a time all the way down to the constant. And for instance, if any of these terms are missing, any of the in-between exponent terms or even the constant, you have to replace them with zeros. So, but then once you do that, all you write is the a, b, c, d numbers, the coefficients of x to the third, x squared, x, and the constant d. You literally just write those numbers down with their signs, plus or minus, as a, b, c, d in a horizontal row, and then take the number that is being subtracted from x in the divisor. For instance, this time it's x minus k. So put k over here to the left of the a. For instance, if this was x minus 3, then we'd have 3 here for k. If this was x plus 2, that would tell us that x plus 2 is really x minus a negative 2, so we would put negative 2 over here. So we always change the sign of what we put here from what we're dividing by. One way to think of it too is x minus k might be a factor of this polynomial, which means then k would be the 0, and so that's what the number we put here is the number that either is or might be a 0 of the polynomial. So here's the process then. Once we set it up, to start the process, whatever number a is, we bring that down to underneath this line right here. We write this line right here, draw this line underneath the ABCD, bring down that number a, whatever it is. Just bring it down. And then multiply k times a and write it underneath b. And so notice we multiplied. And now instead of subtracting like with regular long division, we're going to add. So b plus ka goes right here in this spot right where I'm moving the cursor. And then we take whatever number ends up here, multiply that again times k, and write it up here under c. And then whatever that number is, add it to c, come down to here. And then whatever number this is, multiply it times the k, and write it under the d. And whatever number is going here under the d, you add to d, and so once you get to this last place in the row moving to the right, then that last number that goes right there is the remainder, r. And here's the nice part. We just found out the remainder. For instance, if the remainder happens to be 0, then we know that x minus k does evenly divide into that polynomial if the remainder comes out 0. We also know the answer because these other, in this case, these 3 boxes right here give us the coefficients for x squared, for x, and the constant. And how do I know that? Well, you start at the right. The farthest right number is always the remainder, whether it's 0 or not. Then moving to the left is the constant, and then the x term, then the x squared term, and if you still have more spaces, the x to the third term to the left, x to the fourth term to the left, x to the fifth term. It always works that way. So you actually have your coefficients of your quotient, the answer to the division problem, lined up right here in decreasing exponential order down to the constant, and finally followed by the remainder. Really neat little process. So here's an example of going through it. If we were to divide x to the fourth minus 10x squared minus 2x plus 4 by x plus 3, here's what happens. We're missing an x to the third, so we have to put that in as 0. X to the fourth coefficient is 1. X to the third term is 0. X squared is minus 10. X is minus 2, and the constant is 4. And we're dividing by x plus 3, which is actually x minus a negative 3. And so that negative 3 is what we post out here as the divisor for our synthetic division. We draw the horizontal line here under the 1, 0, negative 10, negative 2, 4 line up here, and follow the procedure. First thing we do is bring down the first number, which is a 1. Bring it down, write it underneath the line. Then multiply. Negative 3 times 1 is negative 3. Then add. 0 plus negative 3 is negative 3. Multiply. Negative 3 up here times the negative 3 is positive 9. And we add. Negative vertically. Negative 10 plus 9 is negative 1. Multiply. Negative 3 times negative 1 is positive 3. Add vertically. Negative 2 plus 3 is positive 1. Multiply. Negative 3 times 1 is negative 3, which again gets posted underneath the 4. Now we add vertically. 4 plus negative 3 is 1, and that's our remainder. So this case, it does not divide evenly. There is a remainder of 1, and the answer is revealed in this lineup of 4 numbers right here, 1, negative 3, negative 1, 1. Because starting to the left of the remainder, going to the left, the first position to the left of the remainder is the constant in the answer. The next one to the left is the coefficient of x. The next one's a coefficient of x squared. And finally, this is the coefficient of x to the third. So this big x to the fourth polynomial divided by x plus 3 winds up equaling then 1x to the third, which is just x to the third, minus 3x squared, minus 1x, which is just minus x, plus 1, and plus the remainder written over the divisor. So plus the remainder 1 over x plus 3. And just as this is, class, right here, just as this is, that's how you input into WebAssign. Your answer to this problem would be x to the third minus 3x squared minus x plus 1 over x plus 3. Okay, so that's synthetic division. Now, we all know that if you divide something by its own factor, the remainder is 0, because if it's truly a factor, that means it divides evenly into it, so you don't get a remainder. The remainder is 0. Now, with polynomials, that is still true. And there's another very interesting fact about polynomials that corresponds to that principle, that if you divide by a factor, the remainder is 0. It's also true that if you plug in a 0 for x into a polynomial expression, if it's a true 0 of the function and you plug it in for x, then you're going to get what y equals when x is that amount. And since it's a 0 of the function, then we know what the answer has to be. Y has to equal 0. So the polynomial function evaluated for that particular value of x being a 0 of the function has to be 0. I trust that makes sense, because if you were to look at the graph of the function at that particular value of x, at a value of the function that was a 0, as we talked a few minutes ago, if it is truly a 0 of the function, then x minus that number is a factor of the function, and that particular x value is the x-coordinate of an x-intercept of the function. And it's always true that the points which are x-intercept points have y-coordinates of 0. So the y is equal to 0 for those given values of x that we call the zeros of the function. And now here's another point that goes amazingly along with that. That if the remainder, if a certain number a, say, is a 0 of a function, then x minus a is a factor. And if you divide the polynomial function by x minus a, the remainder will be 0, just as inputting that amount in for x into the polynomial function will cause the polynomial function to equal 0. Well, amazingly, that's true not just when what you're dividing by is a factor, but it's true no matter what you're dividing by. The remainder is going to be equal to the polynomial function value at that particular value of x, even if it doesn't come out even. This is what the remainder theorem tells us. Here it is. If a polynomial f of x is divided by x minus k, k being some real number, then the remainder, if you divide it by that, is f of k. It's the same thing that you would get as if you just plugged in the number k in for x in the polynomial expression. So if you took f of k, the number being subtracted from x, then f of k is going to give you the same number as dividing the polynomial by x minus k. So the remainder and f of k are the same. And of course, if the remainder is 0, then f of k also equals 0, the remainder. And that tells you that, yes, x minus k is a factor. It divides evenly into it. But the remainder theorem is true whether it divides evenly or not. That's the beauty of the remainder theorem. And of course, when the remainder is 0, it comes very simple here. It turns into another very useful theorem called the factor theorem. It's all these, they're telling you they got proofs on this certain page. You can go access yourself if you would be interested. A polynomial f of x has a factor x minus k if and only if f of k equals 0. So it's got the factor x minus k if and only if f of k equals 0. Now that if and only if class in math means it works both ways. So it has a factor x minus k if f of k equals 0, and also you can state that if it is true that f of k equals 0, then the polynomial also has a factor of x minus k. So it works both ways. And we can use all these things in finding the zeros and finding the factors of polynomial functions. So for instance, if you're using synthetic division, you're trying to test various numbers to see if they're zeros of a polynomial function, you can just do the synthetic division with your potential 0 numbers as x values. And if the remainder comes out to be 0, then you know that that number is a 0 of the function. Or if you just plug in that number in for x into the function, and if the entire expression comes out to be equal to 0, then you know you have a 0 also. And you also know that you have an x-intercept at that particular value of x. Which brings us up now to a very practical, useful test known as the rational zero test. And this is going to be our next to last test, actually, that we're going to talk about in this lesson. We're going to cover the rational zero test here today, and also Descartes' rule of signs. We are not going to do the upper and lower bound rules later in this section. Just to let you know, for those of you who are faithfully reading through the sections in the text, we are not going to do those upper and lower bound rules, but we are doing the rational zero test and Descartes' rule of signs. So here we go, rational zero test. So as I indicated earlier, this lesson, little pause right here, this lesson's a little bit longer than some of the ones that you sometimes have, because I'm actually doing two sections in one here. So this one is going to be in entirety a little bit longer than many of the previous ones, but you know, feel free to cut this off and watch it in two parts if you like, however. But continuing on, then we're going to still go a few minutes more. The rational zero test for polynomials. Once again, what do we mean by rational zero? Well, in the real number realm, there's two types of real numbers, the rational and the irrational. Rational numbers are numbers which either are fractions or they can be represented as a fraction of two integers. That's the definition of a rational number. Irrational numbers cannot be written as a fraction of two integers. It's not difficult, it's impossible, like the square root of 2 or the number pi. Those are irrational numbers. Rational numbers are like 2/3 or 5/4 or -3/4 or the number 2. 2 is a rational number because it can be written as the fraction 2/1. Anything can be written as itself over 1. So all the whole numbers are also rational numbers. And here we go. A nice little test for finding all the numbers that could possibly be rational number zeros of a polynomial function. Here it goes. If we have the polynomial f of x is equal to, here it is with all these a sub n numbers as the coefficients, but it's just a way of representing random coefficient values. A sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus going on and on, like a sub n minus 2 times x to the n minus 2, etc., etc., etc. Anyway, finally, plus a sub 2 x squared plus a sub 1 x plus a sub 0. That's the polynomial. And there's no relationship between those coefficients. They all can be random different numbers, positive, negative, 0, whatever. Then, except the first one can't be 0, the a sub n can't be 0. Now, so if that polynomial has integer coefficients, all the a sub n minus 1, a sub 1, a sub 0, the constant, everything are all integers, they're whole numbers, positive or negative, then every rational number 0 of that function f has the form of p over q, where p and q have no common factors other than 1. In other words, p over q is a fully reduced fraction. And p is a factor, it's an integer factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. So what you do is you find all the factors of the constant at the end of the polynomial, and you call all those factors various different values of p, and you find all the factors of the leading coefficient in front of the term of highest degree, and you call all those possible values of q, and then you divide all the values of p by all the values of q and discard the ones that are repeats, so to speak, in the list. And then that list of numbers that results is the list of all possible rational zeros of the polynomial function f of x. Does not mean they're all rational zeros. Some of them might be, some might not be. They all might be, or they all might not be. You don't know from this. It just means they're all possible. It also means that no other rational zero except those numbers, no other rational number except those numbers can be a zero. So it's your maximum possible list of rational number zeros. Now when we take these possible rational zeros equals p over q, so it's factors of the constant term divided by factors of the leading coefficient, we have to do it both positive and negative. And so here's how this works, class. Example 7, find the rational zeros of f of x equals x to the third plus x plus 1. Well, the constant here is 1. And the only possible factors of 1 are positive 1, negative 1. So as we say, just plus and minus 1. The only factors of this invisible leading coefficient in front of x to the third of 1 are plus 1 and minus 1, the same as the factors of the constant, because it's the same number. And so our possible rational zeros are plus or minus 1 over plus or minus 1. Well, that gives us apparently 4 possibilities. Plus 1 over plus 1, plus 1 over minus 1, minus 1 over plus 1, and minus 1 over minus 1. But we all know that plus 1 over plus 1 and minus 1 over minus 1 are the same. They're both positive 1. So that's what I mean about repeats. And plus 1 over minus 1 is the same as minus 1 over plus 1. They're both equal to just negative 1. So what looks like we're going to get 4 possible rational zeros, it comes out to actually only be 2. And when we test those, you may test these numbers you get as the possible rational zeros. You can test them either with synthetic division. Take the numbers just as they are, the possible rational zero you want to test, just do synthetic division with that exact number as the divisor, including its sign, or take that exact number with its sign and plug it in for x into the function. And that's what they do here, because either way, if it comes out to be 0, or if the remainder comes out to be 0 with synthetic division, then you found a true 0. And so let's do this. We're going to do f of 1 and f of negative 1. Here we go. F of 1 is 1 to the third plus 1 plus 1. Well, that's 1 plus 1 plus 1 is 3. And you can see that 3 is not 0. So the number 1, yes, it was a possible rational zero based on the rational zero test, but it's not an actual 0. Let's try negative 1. F of negative 1 is negative 1 to the third plus negative 1 plus 1. Well, that's negative 1 plus negative 1 plus 1 is negative 1. Well, it's still not 0. So neither 1 nor negative 1, the only possible rational zeros for that polynomial function, neither one of them are actually zeros. And that tells us that polynomial has no rational zeros. And when we look at the graph of the thing right down below here, we see something interesting. It only crosses the x-axis in one place. So let's talk about this for a moment. That tells us something. It tells us, since it crosses it in only one place, but it does cross it, that whatever number that is right there, first of all, we know it's not a rational number, because we've eliminated the possibility of this polynomial even having a rational zero. We just discarded that possibility. So that means it's an irrational number. And since the graph of the function crosses the x-axis at that value of x, that 0 is a 0 an odd number of times, multiplicity of an odd number. It's either a 0 once, or 3 times, or 5 or 7 or 9 or whatever, but it can't be that because we only have an x to the third equation. So it can only be a 0 one time or 3 times. Here's a really interesting point, class, why an irrational number, why this 0 denoted by this x-intercept, the one and only x-intercept of the graph of this function, cannot be an irrational number. I mean, no. The 0 can be an irrational number, but it cannot be 3 times. That's my point. That 1, 0, yes, can be an irrational number. And since there's no rational real zeros, and we've found now one irrational real zero, or we at least know where it is on the graph, that means the other 2 zeros can't even be real numbers, because the graph doesn't touch or cross the x-axis for the other zeros. So that tells us the remaining zeros are complex numbers. Now, that's interesting, because how can that be? If the graph does not cross the x-axis or touch the axis but so many times, but its degree is higher than that number of times, then you know the missing zeros are of complex numbers. Or if the graph just touched the x-axis without crossing it, then one of the zeros could be, for instance, a multiplicity 2. Well, here there's an interesting reason why this particular 0 for this function can be multiplicity 1, but it cannot be multiplicity 3, and here's why. If it was an irrational number of multiplicity 3, when we did the factors, x minus that number times x minus that number times x minus that number, if that number was irrational, then it would force some of the coefficients of the resulting function itself, when you multiply those out, to be irrational. At least one of them would have to be irrational. And I'm not getting into this big time right now, but it tells you, that lets you know that irrational zeros have to come in pairs, just like complex zeros have to come in pairs of their one with the conjugate of the other. It's the pair is going to be one complex number with its own conjugate. That's always going to be how complex zeros come in pairs of conjugates. And irrational numbers have to come in pairs like that. So if you had, for instance, one irrational 0, 2 plus the square root of 3, then you'd know you had another one, 2 minus the square root of 3. Sort of like conjugates of complex numbers. So anyway, we know that this irrational 0 cannot be there 3 times, so it's only there 1 time, telling us that the other 2 zeros, then, since they can't be rational numbers, they can't be irrational numbers, therefore they can't even be real, so therefore they're complex zeros. Now, this little table right here, these 4 points can be very helpful, particularly number 2 and number 4. We're not getting into the intermediate value theorem, so you can skip 3. And most of you probably don't have a programmable calculator, but 2 and 4, good points here. Number 2, in helping you find rational zeros and then subsequently finding factors of polynomial functions, graphing them initially in your work, right off, go ahead and graph that thing, can be very, very, very helpful. It says it can give you a good estimate of locations of the zeros. Yes, that's true, for instance, if they're irrational. But if they're rational numbers or whole numbers, it can tell you exactly what it is. Desmos is very good for this. It'll tell you to 3 decimal places what it is. Now, I will tell you this, if the zeros are irrational, or even if they're rational, and you're using Desmos and you know what it is to 3 decimal places, and you try to put that in WebAssign will mark it wrong. So if the 0, for instance, is the square root of 2, that's what you're going to have to put in WebAssign, not 1.414, which is the square root of 2 to 3 decimal places. It will reject that. So be careful on this. And also, if Desmos shows that the 0 is 0.333, well, that probably means the 0 is actually 1/3, which is 0.33333 forever. Well, if you put that 0.333 in, you will get marked wrong. So be careful how you do this. Try to get your actual fractions and your actual square root answers not just rounded off decimals, because that's not going to give you a good homework grade. And the factor theorem and synthetic division can be used to test. Once you find out what the possible rational zeros are with a rational zero test, you can test them one at a time. You can look at the graph and say, yeah, it looks like it crosses somewhere around x equals 2, and 2 is a possible rational zero, so you test 2 with the factor theorem or synthetic division, and yeah, it comes out, yep, then you know you found a zero. Okay. I've only got one more thing to go over with you here, and this lesson will be concluded on our discussion of 3.2 and section 3.3, and that is Descartes' rule of signs. And here it is. Descartes was the mathematician who made the famous philosophical statement. He said, I think, therefore I am, and he did a lot of thinking. In fact, he discovered this principle about polynomials and their zeros, their real zeros, either being positive numbers or being negative numbers. Very interesting what he discovered here. That if you have that polynomial function again, once again, f of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1, da, 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 all the way down to a sub 1x plus a sub 0. And all the coefficients are real numbers. And the constant, now here's a key, the constant cannot be 0. The constant at the end has to be something other, it has to either be a positive number or negative number. It cannot be 0 for this to work. Okay, but given all that, then here something we're going to know. That this particular function, if it has any positive real zeros at all, the number of positive real zeros is going to be equal. It's going to be equal to the number of variations in sign of f of x, or it's going to be equal to less than that number by a multiple of 2, an even integer. And we're going to look in just a moment what we mean by the number of variations in signs of x. And secondly, the number of negative real zeros of f is equal to either the number of variations in sign of f of negative x, or less than that by a multiple of 2, an even integer. So, for instance, a variation in sign, first of all, means that if you list the polynomial out, as they do above, list it out with descending exponents, not skipping any exponents, starting with the highest one, coming down one, down one, down one, down one, all the way down to the constant. And a variation in sign means that as you move from left to right, and you look at the signs of the terms, a variation in sign means a change in sign. So for instance, with this example 9, 3x to the third minus 5x squared plus 6x minus 4. We start with the positive 3 leading coefficient. Going to the right, the sign changes to minus. That's our first change in sign. Then going to the right changes to plus, our second change in sign. Then it changes to a minus, our third change of sign, our third variation in sign. So the number of variations is 3. That tells us that that polynomial has either 3 positive real zeros or 1 positive real zero. That's 3 minus 2. If it was a long polynomial, say it had 7 variations in sign, then the number of positive real zeros would either be 7 or 5 or 3 or 1. And what about negative real zeros? Last point of the day. Negative real zeros is the number of changes in sign for f of negative x. And that's right down here, class. What does f of negative x mean? Very simply means to plug in negative x for x into the polynomial. So for this one, for instance, it means 3 times negative x in parentheses cubed minus 5 times negative x squared plus 6 times negative x minus 4. And then you process all these signs. For instance, negative x to the third is actually negative x to the third, so it's negative 3x to the third. Sign does change there. Negative x squared is still just x squared, so no sign change there. But negative x times 6 is negative 6x, so that term changes its sign too. And now notice what happened. all the terms in the polynomial for f of negative x are all negative, so there's no changes in sign going from the first term on the left to the last one on the right. No changes of sign. So the number of changes of sign is 0, which tells us that, by Descartes' rule of signs, this polynomial has no negative real zeros. It doesn't have any. It cannot have one. It's very interesting stuff. It cannot have a negative number as a real zero. What if there had been an even number of variations of signs? What if there had been 6 variations of sign in a real long polynomial? Well, if there were 6 variations in sign of f of negative x, then that would tell us that you have either 6 or 4 or 2 or 0. You go down by 2 each time. 6 or 4 or 2 or 0 negative numbers as real zeros. That's what it would tell you. You don't know if it's 6 or 4 or 2 or 0, but it would be one of those. That's how many there actually would be. That's how you use Descartes' rule of signs. And that is as far as we're going to go in this lesson today. This has been just almost exactly an hour and a half. Like I said, a little bit longer than others, but we have traversed our way now through 2 sections. 3.2 about polynomial functions of higher degree, and 3.3 about real zeros of polynomial functions. And in just a couple days, most likely on Wednesday is the plan, there will be another video coming out for the next section of 3.4. So once again, I do hope this is helpful to you, and I leave this with you now, and this will be the end of the lesson. So have a good day here.